back to doing a lot more with really just our entire focus on trig functions, working with trigonometric identities. And what an identity is, in general, is an equation that's always true. So, for example, 2x minus 3 is equal to the negative of 3 minus 2x. You can see why, clearly, right? Like if you distribute this negative, you'll get this expression. In a sense, you could say by distributing that negative, you're sort of proving that that identity is true, right? Not very much work involved, but as a demonstration of its truth. That means no matter what value of x you plug in, this side will always give the same value that side does. We're going to be working with identities that involve trig functions. And so there are some basic definitions of trig functions and how they are related to each other in this top box, like the fact that cosecant and sine are reciprocals of each other, and that's what this pair of equations says, right? Likewise, secant and cosine are reciprocals of each other. That's what that pair of equations says. Tan and cotan are reciprocals of each other, and they are also each have a definition of the ratios of sine and cosine versus cosine and sine, respectively. These are things we've known since last semester, like in Pre-Calc 1, right, when we were just introducing the trig functions. In addition, we have a couple other identities, these three other identities, the Pythagorean identities, and the formulas on this page are the ones that you need to know. You need to memorize them. They will not be provided. However, at least this top group we've needed to know for some time. And I'm going to demonstrate why the ones on the bottom are true. And to be honest, this one right here is always like the one that I always memorize. Like I know that one cold. The others you can obtain from that first one. So let's see why sine squared plus cosine squared is equal to 1. This is not the first time we've seen a figure like this. We're fairly familiar with the unit circle. Here I've really, have dispensed with all the special angles around that we're used to seeing them in order to get some values. We're just really focusing on the fact that on the unit circle, if we, for an angle that we draw in standard position, measured up from the positive x-axis, the cosine and sine of that angle are just defined to be the coordinates of the point where it crosses the unit circle. That's why we can use the unit circle, right, to obtain, sine of pi over 6 as a half. It's because we're just grabbing that y coordinate. So they call it the Pythagorean identity. Why do you suppose they call it that? Yeah. It is essentially an instance of the Pythagorean theorem. So starting from this figure, it might make sense to just drop down a perpendicular, and we'll make a little right triangle. So if I drop down this perpendicular line, so that's a vertical line, what should this length be in terms of using the coordinates of this point? What should that length along the bottom be?
Cosine?
Yes. And how about this one? The vertical side.
Sine theta.
Yep. And what is the length of the hypotenuse? 1, because it's a unit circle, right? The radius is 1. And so using the Pythagorean theorem, right, Pythagoras tells us that cosine theta squared plus sine theta squared is equal to 1 squared. Now let's simplify this a little bit. I've written cosine, we're squaring the cosine function. There's a little shorthand notation for that. Cosine theta all squared is the same as cosine squared theta. We put the, and I know I've probably talked about this before, but just to emphasize, we put the square here because we don't want it to look like we're squaring the angle, right? We're squaring the entire function. Plus sine squared theta is equal to 1. There's the, what we call like the primary Pythagorean identity. As for the others, we can obtain each of the other two simply by starting with this equation. So let's say I take this equation and I divide both sides by cosine squared. Well, that means on the left side, because I have a sum divided by cosine squared, I can split this up. Cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta is 1 over cosine squared theta. Now that first term, cosine squared over cosine squared, that's 1, right? I'm dividing something by itself. This second term here, sine squared over cosine squared, that's a fraction where we squared the top and the bottom. This is really, I can use the rules of exponents to write it as sine theta over cosine theta all squared. And likewise, 1 is the same as 1 squared, right? I think we'd all agree with that. So we could write this as 1 over cosine theta squared. And now we're just one step away. What is sine over cosine equal to? Tangent, yep. So this is tan squared theta. What about 1 over cosine? Secant, so this is secant squared, yep. So there's one of the other two. Now there's only one more of these identities left. So again, I'm just going to start with cosine squared plus sine squared is equal to 1. Now, we started from that equation and we divided both sides by cosine squared in order to obtain this one. Let's do something similar to obtain the other one. Who has an idea? By sine squared. Yeah. Let's divide both sides by sine squared. So we already know that that means we're going to divide all terms by sine squared theta. Now, what is cosine squared over sine squared? Cotan squared. And sine squared over sine squared, well, that's 1. What about 1 over sine squared? Cosecant squared. Yeah. Nice. Fun? Okay, now sketch a graph. No, I said that just for Andrew's benefit. Are there questions on this so far? Okay, so so far here's the I think one of the big takeaways is that the Pythagorean identities are fairly simple to deduce. And we call it the Pythagorean identities for a reason. The other big takeaway so far is that this is the stuff that you need to know. Cold. Make flashcards if you need to. They might help. There's going to be lots of other identities that we're going to introduce in this chapter. You don't have to memorize the other ones. You just know how to use them effectively. These are the only ones that you're responsible for knowing. All right, so a lot of what we're going to do in this chapter is to prove trigonometric identities. Essentially, we're getting practice with knowing the identities, knowing how to use them effectively, and basically combining what we know about the trig functions together with algebra to kind of become somewhat nimble when we're working with these trigonometric functions. And it will come in handy near the end of this chapter when we are working on solving trig equations. So when I'm proving a trig identity, what we want to do is start with one side and show, using algebra and some of the basic identities, that it's got to be equal to the other side. What you don't want to do is treat it like it's an equation already. They're not giving us an equation and saying solve it. They want us to establish the fact. So we don't treat it like an equation and then do the same thing to both sides. We take one side and we perform legal algebraic moves to sort of morph it into the other side. And I usually start with what I like to call like the business side. Like there's a lot to work with. So in this example, I'm going to start by taking the left side. Now, I am not writing equals tan x, because I can't just say that it's equal to tan x. I'm hoping to show that that's true. Right? In the end, after I do a bunch of math, my last equals, I hope, will just say equals tan x. What I want to do is use some of these basic identities, like from the first page, and see what I can't do to transform this. So, for example, I know that cosecant is 1 over sine, and I know that cotan is 1 over tangent. So I could replace these oops, that's an x, not a theta. So far it looks like I'm just making it uglier, but don't worry. We're going to make some progress. So on top, we have cosine divided by sine x. Then we're dividing by this fraction. Dividing by a fraction means we multiply by what? How can I rewrite this? What's that? Flip it. Yeah, we'll just write it as a product. So this would be times tan squared x over 1. Now there's a couple ways we could proceed from here, really. What do we know? What is the cosine over sine function? Say that again. Cotangent. So we have cotan times tan squared. How are cotan and tangent related? Yep. Or 1 over. Yeah, so when I was saying like there's a couple ways to go about this, one of the ways is to say that this cosine over sine is cotan, and then we could say, well, cotan is 1 over tangent, whoops, over tan x, and then we have times tan squared. And then, we can cancel, right? We got a factor of tan on the bottom, we have a tan squared on top, so we just get tan x. And because I have maintained all throughout this process, we've maintained equality, right? Using either basic trig identities or algebra rules. I know that what's on the left side here must be equal to what's on the very right side. And we end with a nice exclamation of victory. Exactly. Now, I mentioned before there was like maybe a couple ways we could proceed. The other way we could proceed once we get to this top line here was to say, well, tangent is sine over cosine. And so, like if we just sort of proceed like, like a choose your own adventure book, right? Turn to page 47 if you want to write tan squared as sine squared over cosine squared. So this would look like cosine x over sine x times sine squared x over cosine squared x. Right, just replacing tan with what we know it is in terms of sines and cosines. And then do the canceling here, right? Cosine cancels with one of those, and Sine cancels with one of these. We're left with just sine over cosine, and guess what that's equal to? All roads lead to tangent. The prove this is an identity thing, or prove that this equation is true. It can take a little getting used to in terms of the fact that we can't treat it like we were given an equation that we can work with. We are not doing the same thing to both sides of an equation, which is what we're really used to when we see an equation at first, and we're really just working with an expression and trying to change it into this other expression on the other side. The nice thing about it, though, is that we at least know what we're supposed to get, right? I mean, they tell us right at the get-go we're supposed to be able to show that it's equal to tan x. So we have a pretty clearly defined goal in most of these problems. Should we try another? Sure. Okay. So we want to show that sine cubed is equal to sine minus sine times cosine squared. Now, if I were working on this problem, I think I'd probably choose to start working with the right side because there just seems to be a little bit more to work with there. And I'm hoping, after a little bit of work, that we're going to be able to show that I'm going to be able to write equals sine cubed at some point along the way. It's not always obvious, how we proceed. In the last one, we really started just by diving into using some identities and making some substitutions. In this problem, what really jumps out at me is I'm subtracting these two expressions, right? I've got sine minus sine times cosine squared. And I have this common factor of sine in both of these. So why don't we just factor it out? And if we factor out the sine theta, what's left in the parentheses? 1 minus cosine squared theta. Now when I start to see squares pop up, especially in terms of like sums and differences, one of the things that really jumps out at me, or one of the things that I think of, because it happens with some frequency, is I should check out Pythagoras, right? Pythagoras is all about relating squares of trig functions together. So Pythagoras tells us, I'll do a little side work here. Pythagoras tells us that sine squared plus cosine squared is equal to 1. Does that afford us any opportunities here? Like, what's something we could do here?
1 minus sine squared theta.
So, like, subtract sine squared theta from both sides? Like, so cosine, if we isolate the cosine squared theta, it's 1 minus sine squared theta. Yeah, we can do that and just sort of use that to replace this whole thing inside the parentheses. Sometimes people look at that and say, you know what, I'll just replace 1 with sine squared plus cosine squared, and then they simplify the result, and eventually it'll just get down to, oh, that's not how it, that is true. That equation's true. Cosine squared is 1 minus sine squared, but I don't think that's the version we want to use.
Sine squared theta equals 1 minus cosine squared theta.
Yeah. Maybe that's the one you said already, but I just wrote down the other one. But yeah, the 1 minus cosine squared, because that's the actual expression that we have in the parentheses. So we can replace the 1 minus cosine squared with sine squared theta. And guess what sine times sine squared is? Sine cubed, yeah. Victory is ours. Exactly. Are we having fun? Okay, good. All right. Another prove the identity problem. So we have to pick a side to start on. What do you think about this one? How about the side that's got all, you're totally speaking my language here. The side that has all the stuff on it. So that means secant squared y over cotan y minus tan cubed y. I can't say it's equal to tan y yet, but we're hoping to get there. No common factors right away that jump out at us. We have a factor of cotan on the bottom. What would this turn into if I bring it up top? Yeah, because it's the reciprocal, right? So we could bring this up as a factor of tan y, secant squared y minus tan cubed y. Who's got an idea?
Factor out of tan y.
That's a good idea. I mean, we can do it. So here's one thing, though, I just want to emphasize. So it'd be secant squared minus tan squared. When we're doing this, like, we work through these examples, we kind of go step by step, and we don't spend a lot of time being stuck, really, in class. It's not always that way. I mean, sometimes you'll find yourself working on a tough problem, and you try things that you're totally allowed to do, but maybe they just don't make much progress. So, I hope part of what I want to emphasize is that these are the types of problems where there's not always like a clear path. We don't know exactly like it's this and then this. It's not very algorithmic, but we just want to have like a list of things we can try, right? And know that if something doesn't work, we can try a different route. Once we're here, I think this is a good route, by the way. When I look at this, I don't feel stuck right now. I've got tan y times secant squared minus tan squared. When I'm doing these, I often keep my eye on the ball, right? We're hoping to show that this whole thing is just equal to tan y, right? So I have a sneaking suspicion that, maybe this stuff should be equal to 1. What could lead us there?
1 by cosine squared y minus sine squared y by cosine squared y.
You mean like translating them into sines and cosines? So that would look like that. Oops. What can we do now? Yeah. Yeah, so like they've already got a common denominator, so that's kind of convenient. So it would look like that. And where can we go from here?
1 minus sine squared y is equal to 1. Or, excuse me, equal to cosine squared.
And why? How do we know that?
Because of the Pythagorean.
Yes, yep. So this right here is equal to this because of the Pythagorean identity. And of course that fraction is equal to 1, so we just get tan of y. You could also have chosen up here at this step to use one of the other versions of the Pythagorean, you know, the two other Pythagorean identities. One of them involves secants and tangents and not sines and cosines, and that would work as well. Okay, questions so far? All right. Okay, so this next one, I mean, I guess we have stuff going on really on both sides of this equation. So just, you know, without a loss of generality, we could just pick the left side maybe to work with. We're hoping to show that it's equal to the right side. There's nothing really obvious that jumps out at us, so I'm going to show you another technique that that can work when we don't have a lot of other options, depending on what the expression looks like. There's no factoring we can do here. We'll just note that, right? There's no canceling we can do because I got that subtraction up top. So if you look at the expression on top, 1 minus sine x, we're no stranger to seeing expressions like this, and we're used to, if we're working with an expression that looks like, I don't know, oops. Let's say if I were working with an expression like 2 over 1 minus 3j, we would know what to do with that, right? If I were working with that when we simplify or when we want to do the division, we say, oh, we can multiply by the conjugate at the bottom, and that often sort of takes care of things for us pretty well. That's a technique we can use to help us wrangle lots of different types of expressions. And it's the fact that I see the 1 minus sine x show up here, that's what tells me, you know what, maybe I'll just multiply by the conjugate of this guy on the top and the bottom. It's a technique that, you know, is not rare, right? It doesn't happen all the time. But I'm on the lookout for it, and when I see an expression that involves like 1 minus sine or 1 plus cosine or 1 minus cosine, like, then I know that that might be a technique I want to use. So now we got some algebra to do. Up top, let's see what this gives us. We have 1 minus sine x, and then 1 plus sine x. Let's FOIL this out. We get 1 minus sine x plus sine x minus sine squared x. And of course the minus sine x and the plus sine x, those cancel. So we just get 1 minus sine squared x up top. On the bottom we've got sine x times cotan x times 1 plus sine x. Now, I feel like we're making progress here. One of the things that makes me kind of feel like I'm maybe at least on the right track is I see that this 1 plus sine x, it introduces a factor of 1 plus sine x, and I do want that to be a part of my end result. There's the 1 plus sine x in the bottom on the right hand side. But we definitely have a little bit more work to do. What is 1 minus sine squared x equal to?
Cosine squared x.
Cosine squared x, and how do we know that? Yep. And what is cotan x equal to? It is 1 over tangent, but I think I think we might make more progress here if we write it as cosine over sine, just because it'll afford me to maybe do some canceling with that factor of sine. So we can cancel the factor of sine here. Now we've got cosine squared x divided by cosine x times 1 plus sine x. Now it's all over but the shouting. What's left to do? Yeah, definitely cancel, I think. And here's how we know, right? Like, I always want to keep my eye on the ball when I'm going through this. So I'm always sort of keeping an eye on what my goal is here. And if we cancel that factor of cosine, then we're pretty much done, right? It's just cosine. We're left with cosine over 1 plus sine, and that's what we wanted. Questions on any of these problems so far? Okay. So a bunch of these problems read like the ones we've just been doing. They want you to prove an identity. Sometimes, though, and these can sometimes be almost harder, not because the steps they require us to take are more difficult, but just because we don't know what exactly the end result is going to be. So this just says simplify, which means we don't know what it's going to end up being, right? At least with the other ones, we have the benefit of knowing what our end result is, or which means we know when we're done, right? When we're simplifying, the good thing to keep in mind is that usually we're trying to see if we can write it in terms of just one trig function, right? Can we simplify it to something that only involves one trig function? So let's begin. We've got cosecant over tan plus cotan. Now, we learned a while back when we were working with exponents and radicals and stuff that sometimes they like to be sneaky and have fractions within fractions, and they try to hide fractions within fractions by using negative exponents, but we could see right through that, right? It looks like we kind of are hiding fractions within fractions here as well. We have tan plus cotan. And just because they are reciprocals of each other, it just seems like an odd way to express that and have that exist in the denominator. So I'm going to start by writing this as just tan x plus 1 over tan. I'm just going to let the fractions within fractions come out of hiding, and then we can deal with it. Now what can we do? I mean, certainly we don't want fractions within fractions, right?
Combine tan x plus the 1 over tan x.
Like add the fractions?
Right.
Sure. So if we do that, how would we, what do we need to do?
Multiply the first tan x by tan x on denominator and numerator.
Yeah. Great. So when we do that, we've got on the bottom tan x. On top we have tan squared x plus 1. Let me draw your attention to this bit right here. Tan squared plus 1. Where have we seen that before? It's secant squared, right? That's Pythagoras. Still got fractions within fractions. What do we do now? Yeah, yep, let's try that. So cosecant x times tan x over secant squared x. Now, I gotta tell you, we definitely made progress in that now we have a single fraction right here, but it still has 3 trig functions. At least it doesn't involve addition or subtraction though. So we're still making progress. We're hoping to boil this down to something that ideally might just have 1 trig function. So one technique that you can always sort of fall back on, especially once we get it to just a handful of factors, there's no addition or subtraction or anything, is just convert everything to sines and cosines and then sort of see what happens with that. So for example, cosecant, we're going to go back to having tons of fractions within fractions in a second, but we'll fix it. Cosecant is 1 over sine x. Tangent is sine over cosine x. And what is secant squared? Yeah, 1 over cosine squared. We can do some canceling right off, right? In the numerator of this fraction, we have a sine and a sine that will cancel. And then we could take this 1 over cosine squared and throw it up top. It's reciprocal. So we have now 1 over cosine x times cosine squared over 1. And now we can really see the end. So cosine cancels with cosine. And we're just left with cosine x. Now that is simplified. A single function. And simplified in that for sure, I mean, I think we would all agree that evaluating just cosine x is a lot simpler. If I know an angle, I'd much rather plug that angle into just cosine versus plug it into that expression to evaluate it. Questions?
Can you break it down into sines and cosines right from the beginning?
Yep. I mean, you're always allowed to do that. The question, yeah, I mean, that's a tough question to answer. I think what you're getting at is, would it be just as easy or potentially easier, or would it be more work? And I guess that the answer is depends on what the problem is. Maybe sometimes it would make it into a little more, more work, but it should always be possible, and you're always allowed to, right? So like the number one rule here is make sure you're writing down things that are true, right?
Yeah.
That's like just to kind of make progress. Sometimes when we think we're making progress, we'll get to a point and be like, oh, it looks like I just sort of went in circles. But as long as I'm not writing down things that are false, right, then at least I'm still on the green. We can sort of reassess. But yeah, you're totally allowed to, and it shouldn't impede your ability to show it just by converting everything to sines and cosines. Other questions? Okay.